but it's going to be recorded, whatever it is that happens. So, how's everybody doing?
Good.
Any questions, comments on anything we've done so far?
Still trying to get my footing. What did we do? Like, what did you talk about after class ended on Monday?
That's a really good question. I have no idea. Monday's a blur. Uh, does anybody, was anybody here? Did anybody stick around and remember? I'll put it this way. What was the last thing you remember doing?
We were doing the like logic gate stuff, and when I had to leave for class.
Okay. So we had gotten into circuit verse. Is that correct?
Yeah.
And let's see, I logged in last time. We established that you were going to create a project with your name.
Yep.
And make me a collaborator. So I guess the question is, are there any questions on that? Is there anything I need to do here for that? I will come to my dashboard and say collaborated circuits, which shows me everybody that's ever collaborated with me and not stopped. But I see, for example, Deb, Mike, Isaac, Jamie. So I'll go through these and see who's there. Not that it matters to you probably, but I'll put those in my favorites. I'll unfavorite these, and then I'll be able to see just your projects in one place. With that, then, I'm going to say, well, I'll probably just my circuits. Yeah, it looks like we made a NOT gate with an input and an output, and saw that circuit verse likes to think of the two binary states as being 1 and 0. But we've agreed that there's nothing magic about 1 and 0. And the machine has no idea what a 1 or a 0 is any more than it knows what a, I don't know, apple or a pig is. So I think what I'll do next, well, I'll say this. This may not make a lot of sense, but it's going to come up sooner or later. In the circuit elements, this is referred to as an input. That is an input from the user's perspective. So like I can click on this to put a 1 or a 0 on this line to this input to the NOT gate. Subtle point, but again, important. While this is an input from the user perspective, it's an output from the circuit's perspective. You're like, what? Much like this is an output, but again, that's from the user's perspective. That's so the user can see it's a 1 or a 0. But that element actually has an input from the circuit's perspective. Because what we're doing is we're connecting the output of this NOT to the input of this output element. Likewise, this user input element has an output that I'm connecting to the input of the gate.
So the input is outputting the 0 through the NOT gate and then inputting it into the 1?
Yes.
Okay.
Yeah. And I say that, and why it's subtle and important, is we can never connect two outputs directly together.
Because there's nothing being inputted?
There's another reason. Why would I not connect two outputs together? Now, I can connect as many inputs together as I want. So I'm going to select this, Control C, Control V, and I'm going to connect this one user input element, its output, to both of these gates.
Is it because you wouldn't have a value?
You're on the right track. Keep going, keep going. That's I'm gonna grab another output here, and no problem. I can change this, and everything works fine. Okay. If I were to disconnect this and connect this to here, it seems fine. And in this particular case, that's okay. But something could go wrong. What would happen if I said this?
Because it's being reversed and not reversed at the same time. Like it's getting both.
It's getting two signals, but it can only take one.
Yeah, and as long as the signals are the same, if they're both zeros and both ones, that's fine. But what happens when you try to combine on a wire a one and a zero? It can't do it. There's no third state. I mean, push back a little. When we get into the hardware stuff, we actually have what we call a tri-state to avoid this stuff. But in binary, there's no state. It doesn't know. This output is trying to make it a one, and this output is trying to make it a zero. So there's a conflicting there. In fact, you know, when I did that, it pops up a little red box down there saying that there's a contention error. And actually, this is saying stack limit exceeded. Okay. I wish those messages would stay there longer. They disappear. It's a pain because you'll see it. It happens a lot. In this case, that is true if I'm connecting those together. But it's also, I have a feedback loop here. So I have a loop, which is why it says it's running out of a stack, and ask me in problem solving about the stack thing. And we'll talk about it there. Unless you really want to. Another day, though. Post it in the Discord or something. We can talk about what this whole stack thing is all about. But for the moment, I'm going to say, yeah, if you get that little yellow box there, it's unhappy about something. There we go. Okay. And so now life is good. So remember that. One rule: never connect two outputs directly together, but you can connect as many inputs together if you want. One output can drive a bunch of inputs. Okay. Then I think what I'll do next before I go further here is if I go to my browser, oh, I'm in my browser. Whew. Rough day. And I say draw.io, also known as diagrams.net. But it's a drawing tool that you can use online. You don't have to create, so it's free. Again, never pay for anything additional in this course, any of my courses. You can use it online, or you can download it and use it on your desktop. There's no logins or anything because it does not store any information on their servers. In fact,
go away. Jesus,
spam. What you'll do is you'll connect the application to some other storage, like your local hard drive, or it could be Google Drive, some cloud thing or something like that. It has a couple neat features that you can share. If you're online with it, you can share it. We could all be in the same drawing trying to draw at the same time, which can be really confusing. But anyhow, I don't like the grid myself. And what you'll notice is, if you zoom out, there's a page view. And I don't know, apparently they don't realize, it defaults to being on. If you want to have it, I guess you can have it, but I would think it should default to being off, because this is 2026. The heck's a page view? Does anybody print anything anymore?
Not really. I mean, sometimes, but not really.
I couldn't tell you the last time I actually used a printer. So the fact that, an 8.5 by 11 piece of paper page doesn't mean anything to me. So I always unclick that. And now I've got a sort of infinite canvas. Okay. Then there are a bunch of libraries over here. That's fine. All we need for what we're doing are some lines. So I'm going to drag out a vertical line and a horizontal line, and they're going to cross. And you're like, great, what did I do? If I just double click, I can select text. So I can type something on here, and I'm going to call this a truth table. Can we see that okay? There's properties over here someplace. Style. Oh, that's the line. I want the text. And I'll bump that up, make that bigger. Okay. So the question is, why 2 lines?
True and false though.
True and false, yes and no, 1 or 0 are binary symbols. Yes. We're going to stick those into the table here. So you're definitely on the right track. The vertical line is going to separate symbols on the left from symbols on the right. Okay. The symbols on the left side will be inputs, and the symbols on the right hand side will be outputs. So copy this. Okay, so I'm going to have inputs on the left, outputs on the right. And then the question is, well, what about the horizontal line? What is it separating top to bottom? And the answer is that above the line are input labels, names. So each input can have its own name. That way we know them apart from each other. And if there are labels or names on the top, any guesses to what's below it? These will be the values of the input. The 1s or 0s, yeses or nos, trues or false. Okay, so if that's the case, what do you suppose is going to be above the horizontal line on the right-hand side? Output labels. And then below the horizontal line on the right-hand side, you guessed it, output values. Okay with that? So then what I'm going to do is I'm going to say, let me copy or draw a couple more lines here, because that is true for every truth table. What will differ is the number of inputs and the number of outputs, and what you call them, kind of like that. So what I'm going to do, I suppose I should probably. I'm going to make a truth table for our NOT gate. Anybody got a picture in their head yet? How many inputs did the NOT gate have?
You can have as many as you want. Because only have one output there.
One NOT gate can only have one input.
Mm.
Now you're right. You can have as many NOT gates as you want, and each one has an input. So I'm just going to call this. Actually, what am I going to do here? I'm going to call it A. And then I'm going to call the output Q. Actually, you know what? I'm going to call the input D. Their names, doesn't matter what you call them as long as we know what they are. But thinking down the road, I'll use D a lot for inputs for data bits and have D0, D1, D2, 3, kind of like that. And then outputs have historically, we use Q for that. It's a convention that we use. Okay. So do we know how many rows are going to be in this truth table? We said the rows below the horizontal line are the values. So D is my input to my NOT gate. How many different values can I put in there?
Into your NOT gate.
Mhm.
You put multiple, can't you? Because you have multiple inputs. Or just one.
But I've only got one input. All right. So, oops. Remember, here's my NOT gate. And it's only got one input. And it's only got one output. So therefore, how many different values can I put input to it?
One.
Two.
At a time?
Oh, I don't know.
Two. No, you're right. You're right. Two.
Oh, cool.
In other, it can either be either one of our binary values, a 1 or a 0, a true or false, a yes or a no. How confusing is this so far?
Kind of.
Okay. Okay. If you're gonna be like, oh, that all makes complete sense, it's logical, I'd be like, oh, okay. I'd confuse things a little bit by saying, let's pick two other names for our values. I think I said, like, what did I say the other day? Probably like rocks and potatoes, or dinosaurs, or what's that?
Tom and Jerry.
Tom and Jerry. So I could make my truth table by saying, okay, I put a Tom or a Jerry in. I think I'm going to go with this for a little bit to just make that point, because I don't know. Do you guys honestly believe me? You shouldn't, because I reserve the right to lie to you at some point, and I will, just to see what happens. So you never know. Okay. But yeah, okay. So we're making a computer that works on Tom and Jerry. What's that?
Stranger things have been done.
Probably. Although now that sounds like a challenge to make this even weirder. Okay, so if it's a not, and I put a Tom in, what do I get out?
A J. Or Jerry.
A Jerry, yeah. And if I put a Jerry in, what do I get out over here?
Tom.
Tom.
Oh, I can.
And so again, this is the idea of the truth table. It tells us, okay, all the possible input combinations, what does each input combination result in?
The other one?
For a NOT gate, it results in the other one, yes. Now, what's that?
I'm talking to myself.
Okay. I do too, so I don't have a problem with that. What are you thinking?
Personally, I was thinking about how this would work for the other gates. I think I figured it out.
Ah, okay. Well, you're probably a step ahead of me, which will happen a lot. I can get rid of this. Okay. But before I go to the other, well, what are the other gates you're talking about?
And or
Yeah, okay. So I said the other day,
That's not it.
ultimately, all we're ever going to have are three, a not, an and an or. Okay. Before I go to the and and the or, though, one step at a time. Could this, and I'll often think of this as a black box. Okay. Because have you ever come across a black box before? Ever heard the term?
Mhm.
Isn't the thing in an airplane?
Yeah, they like save all the information. It's how you know, like how if like a plane crashes, you kind of figure out why. If it was plane error or captain error.
Mm-hmm.
Or Homelander. What?
So the idea of a black box, which ironically, you've probably seen, disasters. They recover the black boxes, but they're bright orange to help find them, locate them. Now, the idea of a black box is because we don't know what's inside, and we don't care.
Is it a Schrodinger's cat kind of deal?
Yes, I suppose, kind of. But yeah, if you I don't know what. Let's say I don't know my speaker here. Okay, what's inside this? I don't know exactly either. I mean, okay, yeah, there's a speaker. There's got to be something to make noise, kind of thing like that, and it's Bluetooth. So there's some electronics in there, but I don't know exactly what's in there. Frankly, I don't care as long as it works. So we'll use this term black box when we have devices, things where we don't know what's inside. We don't care as long as it works. We just need to know, okay, how many inputs does it have? How many outputs does it have? And what do you get out of it for what you put into it? And that's where the truth table comes in. So my question now is there another kind of black box that has one input and one output, but behaves differently? It's not a not.
Like another type of gate. Is that what you're asking?
Say it again.
Like another type of gate?
It could, you could call it a gate. It could be a gate, sure.
Confused on what you're asking specifically.
Based on circuit burst, I'm gonna say no.
Oh, okay. That would be true. Based on Circuitverse doesn't necessarily have others, but that doesn't mean they couldn't exist.
I thought circuit burst was the end all be all.
I thought that was the universe.
Yeah.
Wow. Okay. So the name is problematic, isn't it? I was suggesting that what if we had another black box with one input, one output, but it was not a not?
Those words cancel each other.
So it's got to behave differently. Otherwise, it would be a not. Okay. So how would a not behave? In other words, when you put a tom in, what would you get out?
A tom.
A tom.
Oh, you are talking about what I was thinking. I just
Was it? I get a tom out. Okay. And when I put a Jerry in,
Yeah, Jerry.
I get a Jerry out. Yeah? Now you could call it a not, or you could call it what? Because the name describes the behavior of it in terms of the relationship between the outputs and the inputs. So that's why we said here, the value of Q is not the value of D. Since there's only one input, one output, those were all the possibilities. You could say not, or you could call it what?
You know, something better.
Something better. You could call it anything, but what would make the most sense? How would you describe the value of Q and related to the value of D? Equals? Sure. Equals, same, whatever. I'll go with equals.
Really good at naming things.
What's that?
So we're really good at naming things.
Okay. By the way, this will crop up a little bit. Well, no, I'll just say it now. Why did you call it a not to begin with?
Because
And why did you think not made sense?
Because it wasn't a not case.
Because we started with not.
Yes. Had I not started with a not and I'd started with this, you would not probably have called it a not. You would have called it equals or same or something like that. The lesson behind that is I don't know if I want to do this now or not. I think about it. It's a bit of a rabbit hole. We have this thing we call NAND completeness. Okay. Now, I said we have nots, ands, and ors. What if we put an and a not together? And we called it an and for not and.
just reverse everything you put into the
I thought you put
beginning.
next to each other. I'm sitting here like, how does this count anything?
I'm jumping way ahead. I should probably just stop this. But I'll just say that while I said that we have everything is made from nots, ands, and ors, those are the only three gates we ever have. As it turns out, if you had a bunch of nands, a bunch of nots and ands connecting, you could do everything with those. So we call this NAND completeness, the idea that all logic can be created from nothing more than NANDs. But I would push back and say, well, why do you call it an and? Because it's not an and, which implies that you have nots and you have ands. And furthermore, if you were going to do everything with nands, the first thing you would do is make a not from an and an or from an and or two. We'll do it later. It's just now when we actually do, I'll say, yeah, you remember when? Okay. But back to, is there another type of black box with one input, one output that behaves differently? So it's not a not, it's not an equals.
No. Maybe.
What if I told you there was?
Is it just gonna keep going, like adding more knots to it?
No, it says,
Well, wouldn't a not just be a not?
Yeah.
Yep. Okay.
But you also make that just be difficult.
So,
Waste of time. That's what I call it.
Yeah, true.
so it's got to behave differently. It's just a single gate, if you will, but the output with respect to the input is different than either one of these two. So when you put a Tom in, what could you get out of it?
You can't. We only have two values. You can only get a Tom or a Jerry because you only have two values.
Can you multiply them?
You're making it too hard.
You put a
Okay.
into what?
So if I put a Tom into this black box, what do you want to get out, a Tom or a Jerry? I don't know. I don't mean to sway you. Okay, there. Okay.
Oh, right. We haven't picked favorites yet.
Good point. We will need to sooner or later establish whether we prefer Tom or Jerry. But even without that, for the moment, you tell me, if I put a Tom in, what comes out of this black box? A Tom or a Jerry? Which one?
Tom.
Tom.
Yeah.
But you said it has to be different. And we just already have Tom and Jerry and Jerry.
Right, but when I put a Tom into here, I get a Jerry out. When I put a Jerry into here, I get a Tom out. When I put a Tom into here, I get a Tom out. When I put a Jerry into here, I get a Jerry out. So if I put a Tom into here and I get a Tom out, I've already got that one case covered here. So if I put a Jerry in, I can't get a Jerry out, or it would be the same thing. Ah.
I was confused, and also it didn't entirely click. I was like, it's just the same thing over.
It's a bit of a trick, I admit. And you're like, why would you ever want one of these things? Well, because what would you call this?
Tom gate.
Yeah, it's a Tom. It doesn't matter what you put in, all you ever get out are Toms. May not seem incredibly useful. It's a Tom generator, I guess. I don't know, Now, is there another one?
Yes, there's a Jerry gate.
There's a
The Jerry generator.
Yes.
Oh, hello.
Oh, Deb, I didn't even see you.
My professor.
I snuck in.
Tom and Jerry for the whole class.
Okay, so I'll go ahead for completeness and say yes. We can have a Jerry gate or a Jerry generator, and that means if we put a Tom in, we get a Jerry out, and if we put a Jerry in, we get a Jerry out. Yeah. Okay. Is there another one?
Not in our example.
What about not getting anything out?
Ooh.
Oh.
That's good, but I'm going to push back and say that's not allowed.
So it has to be one or the other.
So we can't put Tom and Jerry into the shredder. Got it.
Yeah, there's always an output. Yeah. So there always has to be an output, which means there always has to be.
Is there always an input?
And there always have to be input values. Yeah.
Okay, then I got nothing.
You're right. There isn't. There are no other possibilities. With one input, one output, we've covered all the possibilities. There's 4 different kinds, 2 of which aren't very useful. The equals has a particular case of not so much for what we're doing, but as like a buffer or a repeater. So you might have like a Wi-Fi repeater. It just boosts the signal. It doesn't change the signal. It doesn't change the ones and zeros. It just boosts them, makes them stronger, kind of thing. Yeah. Or a lot of times we'll have data. Our processor is much faster than your hard drive or your network, so we'll buffer the data between them. Don't worry about that. Yeah. Okay. So if that's the case, then what if I had 2 inputs? So I'm going to copy this. Don't let me sway you too much. I'm just with what they say already. But what that means now is I'm going to have another column of inputs. Over there. I want the labels to be different, so I'm going to call this one D0 and this one D1. So they're different. They're labels. It's fine. What else do I need to change? What else affects this? I have no idea what this thing is going to do yet.
You would need to add your options because would you be able to use TJ and JT?
Ah, yes. So how many rows are we going to have in this truth table now?
So 4 total rows.
There's 4 total rows. And if there is an input, there's an output. We've already just kind of established that. Okay.
But is there only one output?
Yes.
Or is it also okay?
So far, for the moment. Okay. Now here's an interesting thing. Each of the input combinations needs to be unique. Otherwise, you'd have duplicate rows. So how can we come up with all the unique combinations of binary things? It might help. Oh, did you want to say something, Deb?
Is it just kind of keeping it straight in your brain? So you've got you got Tom and Tom, you got Jerry and Jerry. So it would just be Tom and Jerry and Tom. But is there another way to generate that other than just writing out something clear from your brain?
Yes, I think so. Because while I said, oh, we've only got 2 inputs right now, there is no reason that we can't have a black box with 100 inputs. So how many rows would there be? Probably ought to take it a little easier. What if I had, what if I added a 3rd input? Do we know how many rows there would be?
You said rows, so that would be 6.
Or the square.
Ooh.
Goes to the second ballot.
Did I copy that? I don't know what I did here. So what are the answers? I heard 6. Did anybody think something else? Oh, it's crumble. 9. Okay. What if I said neither of those?
Wait, so you can use all 3, like it's not like 3 times 2 times 1, it's 3 times 3 times 3, so it's 27?
No.
So it can be Tom, 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 Jerry, 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 and Springer, 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 but then any combination of the 3 together?
I can only ever
Like
have
what?
Toms and Jerrys.
What is the 3rd one then?
It's a Tom or a Jerry.
Oh, okay. So
Every input can only be Tom or Jerry. That's all I have available. It might
Okay.
help. I was going to suggest. Think of coins. Coins are binary, right? Heads and tails. We could have made a truth table with H and T heads and tails. So if you had 3 coins, how many different combinations? And you're flipping them all at the same time. How many different combinations could you have? The order matters, by the way.
So is it 8
Like,
then? 2 options?
9
Two
or
options.
something.
options?
I think the number is like 9 qubit, something like that.
You said it was about
But the order matters, so
Yeah.
that's complicated things.
Yeah, it's that old permutation combination thing. How about this? How did we, if we think about what happened from here to here, and let's see, Deb, how did you come up with these 4 rows? How'd you come up with Tom and Tom, Jerry and Jerry, Tom and Jerry? Oh, I messed that up. That should have been a Jerry and Tom.
Well, we only have two options, so it was kind of just in my brain, but I know there's a mathematical equation. So if you have 2 variables and you can use each one both, 2 times 2 is 4. So if we have 3 variables, you can use each 2 options. It'd be like 2 times 2 times 2, which should be 8.
Ah. Did anybody else follow that?
Okay, that makes sense. I'm just trying to make it when trying to like exponents kind of, is that what we're supposed to be doing or?
Supposed to. I don't know about that. But if you want to, we can.
Well, if it works.
Well, let's see. Let's try it out. I'm going to take this one over here for the moment. Get that other stuff out of our face. And we have 1 input here. So I've got a 1. Oh, grumble. So So I've got one input. I've got two values for it. So what's the relationship between them exponentially?
Like 2 times 1, you've got 2 options for there?
Maybe I wanted to start simple, but maybe that's actually too simple. If I consider my 2 input black box down here, then I'd say, okay, I'm going to do it again, aren't I? Stop that.
Can I ask, I wasn't in the beginning, the D and the Q, are those just letters that you, variables that you chose for input and output, or does the D and Q mean something specific?
Would someone else like to answer that? It's a quiz.
There's input labels and output labels.
They're just labels that
How's it
are
like-
commonly used.
Yeah. So they're
Thank you.
labels. They're just labels. You're starting to trigger me. I have a rule about that. But anyhow, I'm not going to go down that path yet. Yeah, they're labels. You can call them anything you want. They're only there to identify
Commonly
it.
used variable kind of a thing?
Okay. So my gosh, what was I doing here? Oh, we said in this case we have 2 inputs and we have 4 rows. Ah, gosh. So what's the exponential relationship there? And I'm struggling here, but I'm going to try it anyhow.
Oh, okay, so
We have inputs. You can go ahead. And
when I think about this mathematically, so if I know that I need 2 variables, 1 Tom, 1 Jerry, 2 variables, and I'm using them like the D1 and the D0. So I would do an underscore next to underneath D and an underscore underneath 0. And then for the first underscore, I would say I have 2 variables I can put in there. So if 2 is my option, I would write a 2. And then the next underscore under D0, I also have 2 variables that I can put in there, Tom or Jerry. So I write 2 as well. And then you multiply 2 times 2, and that gives you how many rows underneath D1 and D0 you have as options.
did anyone else follow that?
I think so.
I think so. How about this? So we just said that if I have 1 input, there's 2 rows, 2 possibilities. If I have 2 inputs, there's 4 rows. There's 4 possible combinations. Okay. What if I add a 3rd input?
It's 3 is 6.
It'd be 4 and 8.
Oh.
Yeah, we said it's actually going to be 8. Do you see the pattern?
Because there's
What
2 variables, 2 times 2 is 8.
Yeah. So what happens just
Oh,
okay. If I add another input? So what if I had 4 inputs?
At 16, you double the number from before.
Oh. Because there's 2 possibilities, every time I add them, that doubles the number of combinations. Therefore, yep, go ahead, Kim.
So is it 2? Is it 2 to the power of 4 for the inputs? Then
Yes.
okay.
Well, well, wait a minute. Say it again. I might have.
The 4th power is the amount of rows you need for 4.
For this one.
Yes.
Okay. Oh, so can we generalize that?
So the inputs is the exponent of the 2 options we have.
So what in the world did I do? I got a diamond in there. I didn't want a diamond in there. Actually, take that back. What I want to do is I want to say rows is equal to something mathematically, and that something is going to be based upon inputs. And you wanted to put an exponent in there.
So it'd be rows equals amount of, well, your binomial, so 2,
Rows equals
to the
2
exponent of input.
inputs.
Yes. Oh my gosh.
Oh, sweet Jesus.
Okay. Does that help us out here?
Yes.
Very much so.
Yeah.
So over here then, what we could have done is we could have said, okay, if I started out with, I don't know, whatever this is, okay, and I have one input, and it can either be a Tom or a Jerry. This is where, again, at some point we'll have to figure out that whole preferred thing, but I don't need to for the moment. So if I was going to add another input, we said that this would be D0 and oh, that's amazing. Do you know what just happened?
What happened?
Did you just delete everything?
No. But did you see all that text just span across there?
Syntax error?
No, it wasn't an error. I don't know if I want to go there or not. But
Wasn't looking.
what's that?
It wasn't looking.
I didn't see it.
Can I do it? I don't know if I
I
can.
saw it.
I don't know if I can do it again intentionally or not.
Oh,
Don't break it.
Gosh, how do I do it intentionally? Well, at any rate, we're drawing here, right? Letters and lines and so forth. What does that look like to the computer?
Nothing.
zero. Off and on.
A bunch of binary symbols. Yes, that's all it is. A bunch of them, a lot of them, but that's all it is. So that big span of characters were the symbols that it took to represent something in the diagram. And I wish I could, gosh, how do I think of that? If I select this and said copy, and then I come over here and I say text and I paste, there we go. So what that is a symbolic representation of whatever it was I copied. I'm getting a bit ahead of myself here.
Is that like what it looks like to the computer versus how we see it?
Essentially, yes.
That's kind of like a computer link. That's the computer's version of our like computer link.
That's the computer's language.
What is that?
What's that? Okay, if we look in here.
Oh, why did that come out of that?
Okay, zooming in, that makes a lot more sense.
Well,
I'm questioning where that came from.
So what we're doing is we're seeing a text representation of the binary symbols. And some of it you can recognize, like CMX graph model, C root, CMX cell. And then you see all these percent things, you know, %3 C, %3 E, kind of thing.
I think I get it. I just can't explain it. Very conceptually, I can't put it in words.
I need to stop this. It'll make more sense later on. Yeah.
Should we give names to all our question marks? Because we have a bunch of those everywhere.
Probably. Yeah, the question mark's just sort of a placeholder. Okay, I'm going to get rid of that. Yeah, we'll talk more about that. We don't really need to right now. We've got more than enough on our plate. And so before I actually did that, I said, okay. If I had another input, I'm going to have 4 inputs, right? And my first input that I had is my T or my J. Well, I know I'm going to have those again. And then I'm going to have a new input. I should have made one with all question marks, probably. But the new input is going to be Tom half the time and Jerry the other half. So I said, okay, make that Tom, make that Jerry. Right? And who said, we're doubling the number of possibilities. So I took those possibilities that I had with only one input and doubled them. And then said that, oh, okay, my new input is going to be one of my states for the original and the other state for the double of that.
But is this one a Jerry generator, or is this one going to generate Tom's and Jerry's?
I don't know what it is.
Okay.
And I don't really care at the moment because I'm just worried about, I'm just trying to figure out input combinations. Every black box I have is going to have so many inputs, and then there's always going to be two to the number of input combinations. It's exponential, it grows. Let's try another one. Suppose I was to add a third input here. I'm going to call this one D2. You'll get used to the fact that we can start counting with 0. Okay. So there's 3, D0, D1, D2. How would you enumerate all the possibilities easily?
The first 4 would be all T's and the second 4 would be all J's for the D2. And you just have to copy paste D1 through T0 underneath it.
Yeah, there's two ways to do it, but we said, okay, if we're going to double this, boom, I've got those down here. And then my D2 is Tom for half of them. And Jerry for the other half.
This class ends at 12:40, right?
Probably.
Okay. Well, I have another class after this.
Yeah, so
I'll miss you.
go. And again, just remember this where we're leaving off.
Okay.
So Friday, you can tell me what the last thing you remembered was, and we'll pick up from there.
Sounds good. Have a good day.
So I am still recording. I'll record a few more minutes, I guess, while people are still here, kind of like that. But I will never hold anybody accountable for stuff that happened afterwards. So, do we kind of see a pattern for
Yes.
creating the number of inputs? Right. Okay.
Yes.
Michael, what were you thinking?
So, I was thinking like that. I can't remember. So like when you like, oh crap, I don't know how to explain. It's, my brain already hurts from inorganic chemistry. I don't need it more.
Okay, I'll take it easy, Alex.
I'm sorry.
I think I know what you were thinking. Okay, and you could say, well, okay, if I've got 3 inputs, there's one combination where all 3 of them are T's. There's one and only one combination where none of them are T's. And then the question is, well, okay, how many combinations are there where there's 1 T? One of the 3 is a T. How many combinations are there where 2 of the 3 are a T? To put that a little more mathematically, I can say, okay, here's the one and only one combination with 3 T's, the number of inputs. So how many are there where there's 2 T's, 2 of the 3 are T's? Then how many are there where there's 1 of the 3 are T's? And then this is where there are 0 of the 3 are T's.
Right. So it's 6, 3, 1, 6, 2, 6, 2, 1.
I'm not sure about the 6, 2, 1 thing. But here, I'll do this. I could start. Do you want to actually? I should leave this up to you. Do you want to start with T's or J's? We're getting into that preference thing.
T's.
T's. Okay, so we start with T's. Now, do you want to start with no T's or all T's?
All T's.
All T's. Okay. So I've got 3 inputs. I've got 3 T's. Now the question is, how would you come up with the combinations where 2 of them are T's?
Either.
There's only 2 because it can, well, 3 because it can be the first 2, the last 2, or the outside.
Yes. And you know what? I might actually make it a little more straightforward. If I started with 0 T's. Right? Okay. Because now, what are the combinations? How many combinations are there where there's 1 T?
3.
Three. And how would you think about which one is a T?
Left, right, or middle. Could be.
I like the left to right idea. You say, okay. Or you could do right to left, left to right, or left to right, or right to left. Either way, okay. But if you want to do left to right, which we're probably used to thinking that way, so I'd say, okay, maybe it's the first one that's a T. If it's not the first one, maybe it's the second one. And if it's not the second one, maybe it's the third one. Just kind of going through them one at a time, left to right. Okay, let me do. Okay. Now I've got all the combinations where there are 0 T's, where there are 1 T's in the set. How many are there where there are 2 T's?
3.
Yeah, TJT,
3 because you've got first, second, first, third, or second, third.
JJJ. No, TGG, whatever it is. Yeah.
Okay. Again,
Do you
how do you want to?
only 2 or at least 2?
Only 2. 2 and only 2.
Yeah, 3.
So how do you want to start thinking about it? Which 2 do you want to be T's? I would say do the left to right thing again, right? You say, okay, maybe it's the first one, and then maybe it's the second one. Or it could be the first one
TJT.
and the third one.
And then JTT.
Or it could be that it's not the first one and it's the second 2.
And then you got TTT because that's the other option.
And then we've got the 3 T's, which is TTT. But what I'm urging you to think about is the pattern here, because what if I said, do this for 5 inputs or 6 inputs? You said, okay, we'll start with 1. And if it's not the first one, then it's the second one. If it's not the second one, it's the third one. Okay, that's fairly straightforward. But here, how can we reason this out? We said, okay, maybe it's the first one. That's one of them. I've got 1 more left. So again, that means it could be this one or this one. So I'll say, okay, it's this one and this one. Now I haven't exhausted all the possibilities yet. So I'll say, okay, maybe it's still the first one. And it's not the second one. So it could be the third one. If I had 4 inputs, I'd just keep going. And then since I've exhausted those possibilities, I'll say, okay, it's not the first one, it's the second one. And then if it's the second one, how many more possibilities are there? Well, since there's only 1 more input, it's got to be that one. But if there were 4 inputs, then I would say, okay, it's this one, and that's a J. And then it would
But
be,
you wouldn't go backwards on that, right? So you wouldn't say it's the second one and the first one because you already got the first one with the second one. So you'd
Yes.
have to go forward with that.
yes, exactly. It's one direction, and we're doing it left to right. So there's a pattern there that, like I said, it gets tedious, but I think I could say, do it for 12 inputs. And you'd be like, oh, okay, no problem.
Oh.
In fact,
Oh.
what happened over there?
No, I'm still. This sounds like
Well, so in that case, now that we know the pattern, and it's just time consuming, what should we do? I mean, I realize this is 1200, not 1240, and they blur together, and not everybody in 1200 is in 1240. But once I figure out how to do something, and it just becomes repetitive, I know how to do it. I want to teach the machine to do it, and let the computer do it. Because the computer would gladly crank through thousands of inputs and give you all the combinations. I don't want to do it. But again, that's the beauty of the machine, the computer, is I can teach it to do it. Maybe that'll be the next challenge in problem solving. Okay. I guess I might as well probably stop there. That's good, I guess. We're getting there. Some things you could think about if you want is we said, okay, there are 4 and only 4 one input, one output truth tables. How many unique 2 input, one output truth tables will there be?
There's gonna be 8 again? Is it gonna follow rows or I just fall into a massive trap?
I don't. Should I spoil? Do you want the spoiler? Or do you want the? No, I'm gonna say, just think about it a little bit. You don't.
Wait, can you say that again?
Sure.
There are 4, not 4 inputs. There's 4 what?
There are 4 one input, one output truth tables.
Yes. Okay.
Right. And only 4. Every other black box we came across would have to be one of these 4.
Yes.
Okay. Now we're starting to think about 2 input, one output truth tables.
Mm-hmm.
So the question is, how many unique black boxes, unique behaving 2 input, one output truth tables are there? Black boxes.
It would still be 4 because there's still only one output.
There is only one output, but we had one output
I'm
up
trying
here.
to remember.
There. Yeah, maybe that's a better way. Why were there 4?
Because there's not, Tom, and Jerry. Those are the 4 output options. So it would be the same thing. It would be copy and pasted all the left side, the D1 and D0 would be copy and pasted. I don't know. I'd have to write it out.
We're all right there thinking the same thing. That's why we're
those bottom 2 options would get me. I'd have to write it out and see what it looked like. The bottom 2 outputs.
That's why I'm not going to say it.
Because that changes things.
I'm going to let you think about it, sketch it out, write it out. Yeah. But you are absolutely right. These are the input combinations we have for all of them.
Mm-hmm.
So the only thing that's going to change are the output combinations.
Mm-hmm.
And then the question is, okay, how many unique combinations of those output values are there?
Hold on.
I feel like you were right saying that since there's only one output, it can only be one thing. If there was still only one output.
At a time per black box.
Yeah.
But okay, I'll tell you what, I'll do this.
If it can be a combination in singles.
Let's do an example here that'll get us thinking. Okay, so my inputs are the same. I've always got the same input combinations. Do you want to get a Tom or a Jerry out here? You pick. Jerry. Do you want to get a Tom or a Jerry out here?
What do I want? What if I just want all be Jerry's?
You can have them all be Jerry's.
Okay.
That would be different than this one. So that's 2.
It changes it because we can't just say. Can we just say not and not? Because it's not like a Tom would be a Tom and a Jerry would be a Jerry. But once you start making the combination, then how is it not or not?
figuring out what kind of gate we have.
Oh,
It's just how we define it.
yes. Yeah. We're just defining all the possibilities. It turns out only 2 of them are going to be useful that we're going to keep around. But, you know, it would be good to know about the others.
So we would just say for the not table, TJ input equals Jerry output and Jerry Tom input equals Tom output. So if that's the truth, then it would still just be 4 possible black boxes.
Okay, now you're going to make me do this. I can't resist any longer.
That's a good one.
You too, Mike.
Uh-oh. I opened the, sorry.
Well, I have to invoke a rule. I'm not big on rules, but I do have a couple. And there are certain 4-letter words that I prefer not be used in my presence. Would you like to take a guess at what one of those 4-letter words is?
Can't?
Spoiler. Boy, that's actually a contraction, so I don't think that really counts. But I get the spirit of it. Okay, that yeah, can't. Yeah, we probably ought not use that word. So, spoiler: the 4-letter words are probably not the 4-letter words that you might have thought of immediately. Hey, I get frustrated myself sometimes, and it's like, ah. If it helps, you have used the 4-letter word a number of times today.
Yeah. Did we?
Yes, you did.
I haven't sworn yet.
No, you haven't. But you've used the 4-letter word that I don't want used. Deb, can you explain again what you were saying? How many,
Where I keep coming up with 4 possibilities?
Yeah.
I started writing it out, so I'm trying to wrap my brain around the fact, because when my brain says when I label it not,
Mm-hmm.
because my brain says TJ and JT, well, the output isn't TJ or JT. So when I wrap my brain around not J and T, I have to kind of retrain my brain to just say that's how it is and that's how we're making it. But if we have
Stop.
4,
You said the word.
oh,
She did?
She did.
That?
what 4-letter word did I say, guys? I wasn't listening to myself.
Well, I don't know what you said. I mean, I was listening, but I can't tell what the word was.
Try it again. Just explain again, how you came up with these. The values you came
Sure.
up with.
Well, we already have those 4 black boxes above, and those are the 4 possibles. And so if we just plugged in,
Stop.
plug, must be plug.
No.
No?
No.
Just?
Just. Yes.
Oh, sorry. Yeah.
Because why do we use the word just so frequently? You will be amazed. Students, I get this all the time. They're like, I can't believe I use the word so frequently. In fact, I got a DM last month from a student I'd had years ago saying that, yeah, he was sitting in a meeting counting how many times people were using the word just. So this will stick with you for a while. But why do we say just so frequently? What do we mean? What are we trying to communicate when we use the word just?
Well, in this context, it's saying it's kind of limiting, saying like this is the only thing it can be. So like it just only be this. So like
Yeah. And how often is something only that?
It makes it definite, but it makes it negatively definite.
Mm-hmm. Now, I will say, I have to qualify here. If you want to use the word just as in justice, that's a different story. Okay. But when you're using the word justice, like, oh, this is just a T here. I submit that there are 2 reasons why we do that. One is because we're trying to cover up the fact we don't know ourselves. I don't know. So I just, oh, it's just that. Don't worry about it.
So what I'm getting is like justice kind of being used in place of only. It can only be this. It can only be that.
Yeah, which, like you said, is kind of limiting. And again, when you think about something even reasonably complicated, how often is it only that? Not very often. Again, the more you think about it, the more imaginative you are, kind of thing, that you realize, oh, there's other possibilities. So let's see. One is, yeah, we use it when we don't know what's underneath, and we just want to say, oh, it's just that, don't worry about it. Or we use it when we do know, but we don't want to go into the details. I could explain to you what all those letters were earlier.
Mine was definitely option 1.
So here, we want to know all the details. We want to know what's underneath everything, all the time, kind of thing. So yes, I will start berating you for using the word just.
Okay.
Focus on that then. He's talking about justice.
Well, okay. Okay. So like I said, if you want to use the word just in the context of justice, freedom, or what's the word I'm thinking of? Synonym for justice. But yeah, if you want to use the word in that context, that's fine. I won't yell that.
Okay, good.
But when I ask a question and you say, well, it's just whatever, I'll be like, whoa, wait a minute. Wait a minute. What do you mean? Just that. Like, how many rows will there be for a 4 input truth table?
16.
Exactly. See how quickly you came up with that now. How did you come up with that?
Because we learned it. It's the input, the 2 to the exponent of the input. I remember we rose that. We did that. It's in the thing. Yeah, that.
That's good.
We did it.
And I'd be willing to bet if I ask you in the future, maybe like next week or something like that, you'll be inclined to say, oh, it's just 2 to the 4th. Like everybody knows that.
Like, so is that why you're also missing hair too? Is because people keep saying that, so you just kind of hair.
Pulled it all out.
Yeah.
There's actually, so be careful, because for me, there's always a story behind everything. And there's a story behind my lack of hair. I don't know if you want to hear it or not.
I was just trying to make a joke. Sorry, that was me.
I take no offense to it whatsoever. And that doesn't bother me in the bit. But now I'm going to say it anyhow, I guess. I used to have hair. I have 2 daughters.
Okay, there it is.
Yeah. No, it's still not the pulling it out thing. But my daughters, who are grown now, they're 20, I don't know, 28 and 30. But when they were young, when they were like 10 or 12. Oh, by the way, another thing is I'm cheap. Okay. That's why I'm like, no, you shouldn't have to spend any money on this, because I wouldn't do it. I'm cheap. So when I needed a haircut,
Just let them do it.
as soon as they were old enough, I'm like, you're going to start cutting my hair. And they thought it was kind of cool. And I'm like, I'm not that vain, so it didn't bother me too much that it didn't look great all the time. Kind of like that. But Valerie, which is actually my younger daughter, they're 2 years apart, was cutting my hair one time. And all of a sudden, she started crying hysterically. And I'm like, what's going on? And she said she'd she was trying to cut a straight line and it wasn't straight. And I'm like, really? Don't worry about it. I don't worry about that. So, okay, no problem. Hair goes out. And next time it's Jillian's turn to cut my hair. And she's cutting my hair. And all of a sudden she starts crying hysterically. I'm like, what is going on? And she was trying to cut a straight line across the bottom and the back. And it wasn't straight. So I'm like, there's got to be something going on here. So I looked. And it turns out I have a bald spot in the back. And it was growing. And so the hairline was moving into the bald spot. So it was nothing they did. It was just the fact that, there was this like sort of half moon shaped, crescent moon shaped, bare spot where they were trying to cut. And so I'm like, well, I've got a solution to this problem. And I just shaved it all up. So.
I understand being cheap. My wife's been cutting what's left of my hair for years.
And I haven't had to pay for another haircut since. And I haven't terrorized my daughters with that.
With that.
Okay. Now what? More than you bargained for. So, I will stop here and say, yeah, think about how many 2 input, 1 output black boxes unique will there be?
My question is, do we have to call them not and not? Because my brain can't wrap around that,
No,
and I'm wondering.
I would actually not do that. Not.
Okay.
Call them, and that's the whole point with like the labels and things. Call them whatever makes the most sense to you.
Okay.
Make it as intuitive as possible.
But there can only be one option. Like there has to be a rule to each black box, because if the first black box is TT with an output of J, it cannot also be TT with an output of T. That would be a separate black box.
It's the combination of these output values that has to be unique.
Okay.
So there's going to be several of them
Separate.
where a T and a T gives you a J.
But on the same one, it cannot be a T and T to give you a T.
They cannot all 4 be in this pattern, in this order.
Okay. Just getting my rules down.
When I copied that over here.
Just kidding. The rules down.
When I copied this over here, right now, this is literally a copy of this one. They're the same. Because I get a JT, JT out, JT, JT out. But if I simply change that to now it's different.
Still feels like we're just like determining what gate we have.
The thing that we did earlier applies here. Yes.
Yeah, so that one table would be 16 options instead of oy vey.
Yep. There'll be 16 unique 2 input, 1 output black boxes. Think of all the possible combinations of these 4 outputs. One of the black boxes, they're all going to be T's. Another one, they're going to all be J's. There's going to be a few where there's only 1 T. There's going to be a few where there's 2 T's and a few where there's 3 T's. And when you get them all with no duplicates, they will total up to 16. Why? Where did I pull that number from? It's like deja vu, like we've seen that before. There's, oh gosh. There are 1, 2, 3, 4 outputs, values, that are binary. And so the number of combinations is going to be 2 to the 4th. So for the input rows, we said there were 2 to the number of input rows. And what we're saying here is, in terms of black boxes, there will be 2 to the number of output values, which is also the number of rows.
So, I'll look up the outputs then. Okay, outputs would be 2 to the number of rows.
Yes, yes.
Okay.
Now you just need to say that with confidence. You think through it, work through it enough times, you're like, well, of course, it's 2 to the number of rows.
Okay. Yeah, so typically, reporting output. That's
Oh, well, okay. You can do it this way.
use all my circuit burst names just so they're all in one place. And actually fiddle with the circuits yet.
Yeah, you'll want to somehow figure out an organizational scheme for your files and data and stuff.
Just
Uh,
right now, since I didn't bring my laptop, I was hoping I could do everything on my Pi, but I take up those images.
What? Sweet Jesus, don't do that.
Sorry, I had to take a phone call. What question are we working on now?
It was the same question, which we now have the answer of how many black boxes there will be. And as you said, there will be 16. And so we're just trying to mull that over and be confident.
Gotcha.
And we said that, okay, if the number of rows is 2 to the number of inputs, there's 1 output for every row. And so the number of black boxes will be 2 to the number of rows. Did you follow that?
Yes, thank you.
Okay. Cool. Okay, so yeah, like I said, now it's just a matter of thinking about it enough, using it enough to become second nature, confident. What also would help is it's a little bit tedious, but enumerate all those black boxes, all 16 of them. And what? yeah, yeah, okay, yeah, sure, right.
And then I give you a good old okay.
I heard that. What you can do to make life a little bit easier is you can put them all into one truth table. So you could do something like this and say, there's a second one. There's a couple more.
Okay, so all the output options, all 16 are just lined up right next to each other, so you don't have to keep copying and pasting the inputs into a separate table.
Yeah, yeah. That's just tedious.
That makes
and
it
I don't want to waste your time.
Yeah, because doing this, when we were doing this just for class was already a lot. That's how I'm going to say that very nicely. It was a lot.
Admittedly, yes, yes,
Stop.
yeah. So
Catching things.
I will stop.
No,
now.
not you. It was the computer. It's my battery.
Are we good? Okay, then I am going to disconnect. Deb, have a good day.
Thank you. You too.
And